Good afternoon to all of y'all. In this video, we wish to see what happens when two soap bubbles coalesce isothermally. We have got two bubbles of radius R1 and R2. They coalesce, they form a single bubble of radius R. The surrounding temperature is T0, the atmospheric pressure is P0, and the surface tension of the soap film is sigma. It is given by Newton per meter, sigma Newton per meter. That is the unit of surface tension. We would now like to ask these following questions. Is mass conserved? Is radius conserved? Is volume conserved? Is surface area conserved? Is energy conserved? Firstly, let us ask whether mass is conserved. We are assuming that when the two bubbles coalesce, they come and join together and their common wall is broken and the air mixes and forms into a bigger bubble, into a single bubble. We don't know whether it's bigger or smaller, but into a single bubble. So we are assuming that there is no leakage of air outside or no outside air comes in. So in fact, mass will be conserved. So if the mass of this is m1, if the mass of this is m2, if the mass of this is m, we can say m1 plus m2 equal to m. Now if you divide the mass by the average molecular weight of air, you will get the number of moles. If the number of moles here is n1, if the number of moles here is n2, if the number of moles here is n, we can conserve the number of moles and say n1 plus n2 equal to n. We can say this. Now for the radius. Can we say that the resulting radius r is r1 plus r2? No, that will not be the case. We will mathematically see that it doesn't turn out to be that. So this will not be the case. R1 plus R2 will not be equal to R. Is volume conserved? Can we say if the volume of this is V1 and this is V2 and this is V, can we say V1 plus V2 equal to V? V1 here is of course 4 by 3 pi R1 cube. V2 is 4 by 3 pi R2 cube. V is 4 by 3 pi R cube. Can we say that the volume is conserved? Well, it turns out that the volume increases. In fact, because the volume increases, the air inside the bubble does work on the air, on the atmospheric air. So, we are going to see that. So, is volume conserved? The answer is no, it is not conserved. In fact, volume increases. That is delta V is positive, increases. Delta V is positive. So, if you call the volume V is greater than V1 plus V2, we will see this. Why this is so? V is greater than V1 plus V2, that is delta V is positive. V minus V1 plus V2 is delta V, the change, the final minus initial is delta V, that is positive. Then the next question we would like to ask is whether surface area is conserved. That is, can we say if the surface area of this is S, if the surface area of this is S and the surface area of these two are S1 and S2, what we mean here is surface area is 4 pi r1 squared, but of course we will be considering the surface inside also. So this will be 8 pi r1 squared, this will be S1 will be 8 pi r1 squared, S2 will be 8 pi r2 squared, S will be 8 pi r squared. So we are asking the question whether S will be equal to S1 plus S2. Not necessarily. There is one special case where S is equal to S1 plus S2. That is the case when the bubbles are coalescing in vacuum. That is, there is no atmospheric pressure, there is no material outside. If there is no material outside, even if the bubble expands, the bubble does not do any work, because whenever their work is done, there is a transfer of energy. So, transfer of energy from one body to another body. Now, if there is nothing outside, energy cannot be transferred to nothing outside. Yes. So, therefore, if the bubbles coalesce in vacuum, we will see that this is in fact true. Otherwise, S will not be equal to S1 plus S2. In fact, the surface area will decrease. Why are we saying this? Why are we saying this? Surface area, why we are asking this question about surface area is, the surface area of a liquid stores surface potential energy. Now, surface potential energy divided by the area is called as surface energy. This is in joule per meter squared. This surface energy is numerically equal to surface tension. Numerically, both are the same. We will not go into the proof of that. It is a well-known result that surface energy and surface tension are numerically the same. Dimension-wise, they are the same. As you can see, joule is Newton meter. So, Newton meter per meter squared will be Newton per meter. Newton per meter. So, the surface energy is sigma. So, surface potential energy would be sigma into the area. The surface potential energy is equal to sigma into the surface area. So, when we ask the question whether S is equal to S1 plus S2, what we are basically asking is whether the surface potential energy is conserved. Why? If you multiply this throughout by sigma, you will get sigma S is equal to sigma S1 plus sigma S2. This is the surface potential energy before coalescing. This is surface potential energy before coalescing, and this is the surface potential energy after coalescing. So, when you say the surface area is conserved, indirectly you are saying that the surface potential energy is conserved. As we shall see, the surface potential energy will not be conserved. In fact, there is only one special case where it is conserved. As we said, when the bubbles coalesce in vacuum, the surface area and hence the surface potential energy will be conserved, otherwise not. In fact, the surface area and the surface potential energy will decrease. Let us try to understand this with a simple example. Supposing I have this pen, I drop it. It goes down. What is the explanation we give? We say there is a gravitational pull of the earth and so it has gone down. Another explanation is that this body tries to minimize the potential energy. So when it goes down, the potential energy minimizes. So we say systems try to minimize their potential energy. So similarly, surface potential energy also tries to get reduced or minimized. So that is possible only when the surface area decreases. So we will find that in fact the surface area will decrease. Now the next question we are asking is energy conserved? Now one is the surface energy, surface potential energy. That we saw is going to decrease because the potential energy has a tendency to decrease. Left on its own, any body will try to decrease its potential energy. So any system will try to decrease its potential energy. So the surface potential energy is going to decrease. What is the other energy? The other energy is the internal energy of the air inside. The internal energy U is given as NCVT. N is the number of moles, CV is the molar specific heat at constant volume, and T is the absolute temperature. Now, since we are saying that the surrounding temperature T naught is T naught and the system is isothermal. The coalescing is happening isothermally, the temperature doesn't change. So the initial internal energy is N1 CV T naught plus N2 CV T naught. So if you add up these two, you will get N1 plus N2 CV T naught. N1 plus N2, we said the number of moles is conserved. So this will be N CV T naught. Hence, the internal energy will N CV T naught is nothing but the internal energy of the air in the resulting bubble. So therefore, internal energy will be conserved, but not the surface energy. Now let us see the mathematics of this. Let us see mathematically how we can understand these ideas. First of all, we will take the basic conservation of the number of moles, basic conservation of number of moles. So I can say N1 plus N2 is equal to N. I can say this. Now I'll use the ideal gas equation. The ideal gas equation is PV equal to nRT, where for us this P will be the pressure inside the bubble. The pressure in, and so therefore we can say from this N is equal to PV by RT. So for N1, we are going to put the pressure inside the first bubble by the volume V1 by R T naught. N2 will be P2 into V2 by R T naught. This will be equal to P into V by R T naught. Yes. So now you can cancel the R T naught throughout. That will go. Now the pressure inside. Now we have learned that there is excess pressure inside the soap bubble. So the pressure inside would be P naught plus 4 sigma by R1 into V1. Yes? 4 sigma P naught plus 4 sigma by R. 4 sigma by R1. Sigma is the surface tension. 4 sigma by R1 is the excess pressure. Pressure outside is P naught. So the pressure inside is P naught plus 4 sigma by R1 into V1. V1 is given by 4 by 3 pi R1 cube. Similarly, we can write the pressure for the second bubble P naught plus 4 sigma by R2. And here we can write P naught plus into V2. Here we forgot that into V2. That will be equal to P naught plus 4 sigma by R into V. Now you can get what is the resulting radius out of this. If you put V1 as 4 by 3 pi R1 cube, V2 as 4 by 3 pi R2 cube, and V as 4 by 3 pi R cube. R1 is given, R2 is given, sigma, everything is known. So the only unknown is R. The only unknown is R. This can be solved. You can solve for this equation and get what will be the value of R. The equation is slightly complicated because you are going to have a R cube and an R squared term. So R cube and R squared, yes. So it's a bit complicated. Anyway, we will not go into that. But we are simply saying that given R1 and R2, we can find what will be the radius R of the resulting bubble. Now we shall do a small manipulation which will introduce the surface area now. we shall introduce the surface area. To do that, let us see that the volume of a sphere is 4 by 3 pi r cube, and the surface area, here the surface area of a sphere S is 4 pi r squared. The surface area is 4 pi r squared. So therefore, we can basically get what is the ratio V by S. V by S would be R. V by S would be, R by, V by S would be R by 3. V by S, 4 pi cancels, R squared, R cube by R squared is R, there is a 3 here. So V by S would be R by 3. We can do one thing here. We can, instead of putting this as 4 pi r squared, I'll put this as 8 pi r squared, because the surface area that we are going to consider is outside as well as inside. So I'll put that as 8 pi r squared. Now if you did the division, you will get r by 6. R by 6. So I can say the volume divided by the surface area is R by 6. Now what we are going to do here is multiply this. This will be P naught into V1 plus 4 sigma by R1. Instead of V1, we are going to put, we will have V1 by R1, 4 sigma, we will have 4 sigma into V1 by R1, and here we are going to have P naught V2 plus 4 sigma V2 by R2, and here you will have P naught into V plus 4 sigma into V by R. From this equation, we can say V by R is S by 6. So wherever that is V by R, we are going to put surface area by 6. So I will have here P naught V1 plus 4 sigma into S1 by 6. Surface area I have taken as S1, S1 by 6 plus P naught V2 plus 4 sigma S2 by 6. That will be equal to P naught into V plus 4 sigma into S by 6. Now, what we shall do is we can cancel this. This is 2, 3, 2, 3, 2, and 3. I'll group all the surface area terms on one side and all the volume terms on the other side. So let me get all the surface area terms on this side. So I will have 2 sigma by 3, 2 sigma by 3. I have S1 here plus S2. Bring that S here minus S. This is equal to P naught into V. Bring this V1 and V2 to this side minus V1 minus V2. Yes. Now, this V is the final volume, this is the initial volume. So V minus V1 minus V2 is nothing but delta V. This is delta V. Whereas this will be minus delta S, because we are saying initial minus final minus initial. Delta S is S minus S1 plus S2, and delta V is V minus V1 plus V2. So therefore, this becomes 2 sigma by 3 into minus delta S equals P naught into delta V. So I can now say delta V by delta S is equal to delta V by delta S equals minus 2 sigma by 3 P naught. Yes, minus 2 sigma by 3 P naught. Now, let us see the physics behind this equation now. We said that the surface area must decrease. So, delta S is negative because every system has a tendency to decrease the potential energy. So, delta S will be negative. If delta S is negative, okay, this minus and minus goes, delta V will be positive. That is, the volume of the resulting bubble is more than the sum total of the volume of the two bubbles. Initially, whatever volume the two bubbles are having, the resultant volume is greater. That is, the air inside the bubble does work on the air, on the atmospheric air outside. So delta V is positive. Now, if it does work on the uh, atmospheric air outside, if the bubble does work on the positive, if the bubble does positive work on the atmospheric air outside, why do you say positive work? Because it is expanding. Any expansion is positive work. So there is a transfer of energy from the bubble to the atmosphere. Where will that energy come from? It has to come from the surface energy, surface potential energy. The surface potential energy therefore reduces. Therefore, the surface area must reduce. That is why you are having delta S as negative. Now, let us take a case where the system is happening in vacuum. In vacuum, instead of this P naught, we will put 0. If you put P naught as 0, you will get delta V into 0 as minus 2 sigma into delta S, or delta S is 0. Delta S is 0 means there is no change in the surface area, or there is no change in the surface potential energy. This is quite expected because even if the volume changes, because there is no matter outside, when you say the bubbles are coalescing in vacuum, there will be no transfer, there cannot be any transfer of energy to a, of course, if there is radiation or something like that, there can be a transfer in vacuum, but such things are not happening. There is no radiation or anything like that which can travel through vacuum, so there is no transfer of energy to the outside atmospheric air. So therefore, there is no change in the surface area, yes, or the surface potential energy. Now delta S is 0, I can say 8 pi r1 squared plus 8 pi r2 squared is equal to 8 pi r squared, or r1 squared plus r2 squared is equal to r squared, or r will be equal to root of r1 squared plus r2 squared. That will be the resultant radius. So again you see r is not r1 plus r2. So the radius is just not conserved. Yes. But here the surface area is conserved if the bubbles coalesce in vacuum. Thank you.